Welcome to problem set 18. Our problems today will be from the topic chirality, stereoisomers, and Fischer projections. Before we get started with that, just a quick reminder that the worksheet to accompany this problem set is available online through my website. And with that said, let's go ahead and get started with number 1. Number 1, draw 1,3-dibromobutane in a proper Fischer projection below and then complete A through C. So first, let's just draw the molecule not in a Fischer projection. So it's a butane, so 1, 2, 3, 4 carbons. The 1 position and the 3 position will each have a bromine. So the 1 and the 3, and everything else is just hydrogen. So I'll put lines to all those hydrogen. And I just have 1 chiral carbon. I'm going to put a little red star next to my chiral carbon. And because we just have 1 chiral carbon, that means that our Fischer projection will just have 1 intersection, because remember that intersection, that point there, that represents a chiral carbon. We only have 1 of them, so we just want 1 intersection in this drawing. All right, so this is the carbon that's at that intersection. So then we want all these 4 different substituents about that intersection. So I'm going to put the CH3 at the top, so I'll put a little check here. That's the one I've indicated right here. And then we have our chiral carbon, which has a bromine. So I'll put a little check here, and a hydrogen. So I'll put a little check here. And then at the bottom, we have a CH2, CH2, Br. CH2, CH2, Br. Okay, so 1, 2, 3, 4 carbons and a bromine at the 1 and the 3 position. So 1, 2, 3. So counting it backwards there. All right. So A says to draw the mirror image molecule just to the right of your first drawing. So I'm going to put my mirror here. And this is part A. To draw the mirror image form. Because we drew this in a Fischer projection, that's nice and easy to do. We just draw our chiral carbon and keep everything the same, except we're going to make this a mirror, so the bromine is going to be on the opposite side in our mirror image, and the hydrogen as well. So that's part A. Part B, how are these 2 molecules related? Okay, so they are mirror images. They are non-superimposable, because if we try to superimpose this way by just laying it over top, notice the bromines are on the wrong side. If we try to correct that by flipping this on top of the other, notice then that our Fischer projection is no longer going to have the vertical bonds going away. If you flip it, they're going to be coming out at you, which is going to be opposite of the molecule on bottom. So they're going to be going in the wrong direction. Same thing with the horizontal bonds. And then if you try to rotate it this way to get the bromines to line up, notice that your CH3 is going to be on the bottom in one of the molecules, so it's not going to line up with the CH2, CH2, Br. Okay, so they are not the same. They are non-superimposable mirror images, which are known as enantiomers. All right, part C. What physical property will be different for these 2 molecules? So we learned in tutorial 18 that enantiomers will have all the same physical properties except for 1, optical activity. Remember that their optical activity will be in opposite directions. Same number of degrees, but in opposite directions. So one will be to the right, the other will rotate plane polarized light to the left. So for C, That different physical property is optical activity. Okay, let's go ahead and erase number 1 so that we have room to go on to number 2. Okay, number 2. There are 3 stereoisomers of 2,3-dibromobutane. Draw all 3 below in proper Fischer projection and complete A through D. All right, so again, let's start out by just drawing it, not in a Fischer projection, and then we'll convert that into a Fischer projection once we know how many chiral carbons we have and how many crosses to make. All right, so it's another butane, so 1, 2, 3, and 4. But this time we have a bromine at the 2 and the 3 position. So here and here. All the rest are hydrogen. Okay, so our chiral carbons then, I'm going to mark with the red pen, once again, 4 different substituents about this carbon and 4 different substituents about this carbon. So when I draw my Fischer projection this time, I'm going to have 2 crosses, 1 for each chiral carbon. So we'll put a CH3 at the top for this guy, and then we have our chiral carbon here with an H and a bromine, so this hydrogen and this bromine, followed by another chiral carbon with a hydrogen and a bromine. So that's that hydrogen and that bromine. And then at the bottom, that's not a chiral carbon, so we're not going to put a cross there. We're going to just write our CH3 for that achiral carbon. All right, so hopefully you notice already that the way that we've drawn this particular stereoisomer, it does have an internal symmetry plane, which means that although it has 2 chiral carbons, the molecule as a whole is achiral. So if we try to draw its mirror image, we'll just be drawing the same molecule. It will be superimposable with its mirror image, therefore they will be identical. So instead of drawing its mirror image, let's think about another stereoisomer for this molecule. Remember that that means it has to have the same molecular formula and same connectivity of atoms, but a different 3-dimensional arrangement. Okay, so we're going to flip one, but not the other, so that one of these bromines will be on the left and the other will still be on the right. All right, so 2 crosses for our 2 chiral carbons. We've got a CH3. Let's flip the top one, but not the bottom. And CH3. Okay, so there's another stereoisomer for 2,3-dibromobutane. And then this particular molecule does not have an internal symmetry plane. Its mirror image will be a non-superimposable mirror image form. So let's draw the mirror image. CH3, the hydrogen reflects there, as does that bromine. The bromine and the hydrogen reflect here, and then CH3. Okay, so make sure that you are thinking of these Fischer projections correctly, and that is that you're thinking of the backbones as having that C shape like we talked about in the tutorial. Okay, so everything in the vertical is going away from you. That gives the carbon backbone here a C shape, okay, that's pointing into the plane of the whiteboard. And then everything here is pointing out toward you. Horizontal is coming toward you to hug you. Remember, it will hug you. All right, so if you try to superimpose these by laying them one on top of the other, of course your bromine are not going to line up. They're going to be on the wrong side. If you try to rotate it this way and line them up, same thing's going to happen. Your bromine are still going to be on the wrong side. So a lot of students think, oh, well, I'll just flip one of them like that so that my bromines will be on the correct side. Remember that if you flip it, if you flip one of these to get the bromines on the correct side, that you're taking it out of Fischer projection, and now your C-shaped backbone is going to be facing toward you, and those C-shaped backbones are not going to line up. Okay, so that is not going to make them superimposable. They are still non-superimposable mirror image forms. All right. So for part A then, I think we've got all three of our stereoisomers. So part A, circle the two molecules that are a pair of enantiomers. Well, enantiomers are non-superimposable mirror images. So that would be these two here. So I'm going to circle these two. Those are my enantiomers. So I'll write C above. So I circled them above. All right, part B. How is the other molecule related to those two enantiomers? So how is this molecule related to these two? Well, it is definitely a stereoisomer. It has the same molecular formula, same connectivity of atoms. They differ three-dimensionally in space. They are not enantiomers though. This is not an enantiomer of either of these molecules. Remember, enantiomer refers to a pair, and this is the pair already. So stereoisomers that are not related as enantiomers, remember, are called diastereomers. So this is a diastereomer of the two enantiomers. And part C. Which of the above will be optically active? Remember that chiral molecules interact with light and cause that rotation. So only the chiral molecules will be optically active. That is the pair of enantiomers. This molecule had the internal symmetry plane, which meant that even though it had two chiral carbons, overall this molecule is achiral and superimposable with its mirror image form. It does not exist as a pair of enantiomers. So for part C, only the enantiomers will be optically active, and their optical activity will be the same magnitude but in opposite directions. Part D, draw a line under the molecule that is a meso compound. So for part D, let's go to the blue pen and I'll write C above. We're going to draw a line under the meso compound. Remember that the meso compound is a compound that has the chiral carbons but contains an internal symmetry plane and is therefore achiral overall, and that's the first one that we drew here. All right, let's erase number 2 and go on to number 3. Okay, number 3. There are 4 stereoisomers of 1-bromo-4-chloro-2,3-butane-diol. Draw all 4 below in proper Fischer projection and complete A through C below. All right, so once again, let's draw it first, not in a Fischer projection, figure out where the chiral carbons are, and then we'll know how many crosses to make for our Fischer projection. So it's a butane once again, so 1, 2, 3, 4 carbons. At the 1 position, we have a bromine. At the 4 position, we have a chlorine. And at the 2 and the 3 position, we have alcohol functional groups. So I'll write them up. Everything else is a hydrogen. I'm just going to draw lines to my hydrogen. Okay, so if you're looking for your chiral carbons, you're looking for the carbon that are attached to 4 different substituents. So this one here is attached to an OH, a CH2Cl, a hydrogen, and a CHOH, then a CH2Br. So 4 different substituents about this guy. Same thing over here, 4 different substituents over here as well. So 2 chiral carbons. So 2 crosses in our Fischer projection. All right, so we're going to put this carbon at the top, so it's achiral. So we're going to write CH2Br for this carbon here. For the next carbon, we're going to write a hydrogen and an OH. And I should mention, it doesn't matter which order you put these in. If you put the OH over here or over here at this point, because we're trying to draw all 4 stereoisomers. So it doesn't matter which one you draw first. All right, so we've got the OH and the H right here. And then our next chiral carbon is here. And I'll just put them on the same side. OH and H. And then an achiral carbon, so CH2Cl for that last achiral carbon there. All right, we're trying to draw all 4 stereoisomers. This molecule does not have an internal symmetry plane. You might at first think, oh, it doesn't have one there, but it doesn't. The bromine and the chlorine are not going to reflect in an internal symmetry plane here. Okay, so there's no internal symmetry plane in this molecule. That means that its mirror image should be non-superimposable with it. So let's try to draw its mirror image form. Draw a mirror here. Cross, cross, reflecting. Okay, and once again, remember that we are in Fischer projection. So those carbon backbones that we have here are pointing, they're C-shaped, okay, and they're pointing into the plane. Remember, everything on the vertical is going into the plane. So we've got a C shape for these carbon backbones. And everything on the horizontal is coming out at you. That's what a Fischer projection means, okay? So when you try to superimpose these, you might say, well, I think that those are the same. I think that if I, move that over there, I can get those to superimpose. There is no way to get these two to superimpose. If you move this one directly on top over here, the OHs will be on the wrong side. If you try to flip it, then your bromine will be on the wrong side. If you try to take it and flip it this way, then your carbon backbones are pointing the wrong way. Okay, so no way to orient this such that the two will superimpose. They are not identical. They are related as non-superimposable mirror images. All right, well, we have 4 stereoisomers, so let's keep going. For the next stereoisomer, we're going to flip one, but not the other chiral stereogenic center. Okay, so again, 2 crosses, CH2Br. And with respect to the first stereoisomer, let's flip one, but not the other. Okay. So now the OHs are on opposite sides in our Fischer projection. Now let's draw the mirror image, because I don't see any internal symmetry plane within this molecule. So the mirror image should be non-superimposable, another stereoisomer. So CH2Br, my hydrogen reflects. Now my OH here to reflect, and the CH2Cl. And again, any way you try to lay this one on top of this other one over here, no matter how you move it, it's never going to superimpose. So obviously if you lay it straight over it, the OHs are going the wrong way. If you try to move it this way, the OHs are still going to be going the wrong way. If you try to flip it and lay it so the OHs do go to the correct sides, you're going to have your carbon backbone going the wrong directions, and actually your horizontal as well. Instead of coming out at you, they'll be going away from you in the one that you took out of your Fischer projection. So they're not going to superimpose. So these are non-superimposable mirror image forms. And if you have a set of models, I highly recommend that you use it when you're going over stereoisomers. It will just really save you a lot of confusion to build the models and put them in the Fischer projection, so you can really see how those will not superimpose. Manipulate them, try to move them around, you won't get them to superimpose. All right, so we've got all 4 of our stereoisomers. A says to label one pair of enantiomers with a capital A. Okay, so for part A, I'm going to get the blue pen. So we already know that these are non-superimposable mirror images. So this is a pair of enantiomers. I'll label them as A. I'll do it like this. Pair A. And label the other pair of enantiomers with a capital B. So we already said that this pair is a non-superimposable mirror image. They are non-superimposable mirror images. So let's label those as B. Those are the other pair of enantiomers. And part B says, how are molecules A related to the molecules labeled as B? Okay. So we know that these are enantiomers because they're non-superimposable mirror image forms. But how would this be related to this one over here? So that's the question. How is one of the enantiomers from A related to one of the enantiomers from B? How are those related? Well, they would not be mirror image forms. So they would be stereoisomers that are not mirror images, which means that they can't be related as enantiomers. The word that we have to describe the relationship between stereoisomers that are not enantiomers is diastereomers. So either of A would relate to either one of B as a diastereomer. Okay. And last but not least, part C. Which of the above will be optically active? Because they are all chiral, they will all be optically active. Remember that chiral molecules will interact with light and cause it to be rotated. So all chiral molecules will be optically active. So for C, all of them. They are all going to be optically active because they are all chiral. There are no meso compounds here that would cause one of these molecules to be inactive. They are all chiral. They are all optically active. All right, that was kind of a short problem set, but we are through with all three of our problems from problem set 18. So I hope that you will consider tuning in to tutorial number 19. Thank you very much.